Welcome back, students. So in this tutorial we are going to study about fitting an infiltration model. As we have learned already, there are Horton's, Kostyukov and Phillips, and there's green amped model. So in this tutorial we are going to learn how to model the infiltration out of the data that we have got from a field experiment. So let me quickly explain you how the data is acquired through the field experiment. So as we have already seen in the lecture, there is single infiltrometer and double infiltrometer. I also explained you about the dimensions and the working of this infiltration model, infiltrometers. So basically we are going to add some water, and over the time we'll observe how much water is getting infiltrated. So if we plot the infiltration data versus the time, cumulative infiltration versus the time, we are going to get this kind of curve. There's the cumulative infiltration. So the Kostyukov equation in fact gives us the equation to model this cumulative infiltration. Understand the difference. Infiltration is measured in mm. Okay, it's how much infiltration has occurred in particular duration of time, so it is in mm. Infiltration rate is it's measured in mm per hour. So that is in fact the slope of that curve that you see here. The slope of this curve represents the infiltration rate. Okay, Horton gives us this infiltration rate. The Horton's equation represents the infiltration rate at different time. Kostyukov equation gives us the cumulative infiltration. Okay, so that's the difference here. So let's go to the question and see what this question asking us. So okay, before that, let me quickly run through this diagram. So as you can see, the rainfall can be represented as an heatograph, and infiltration, as I have already explained to you in the lecture, that initially the infiltration rate is going to be very high and gradually decays, and finally it reaches a steady constant infiltration rate. So this is the infiltration rate. It is also the derivative of cumulative infiltration. Okay, from the earlier diagram here, if you find the slope at different point, and whatever the slope you got it, if you plot that with respect to time, you're going to get this curve. So Horton has given the equation to model this curve. Okay, so according to Horton, f of t here represents the infiltration rate or infiltration capacity. Infiltration rate and infiltration capacity is one and the same thing. Here, if you look at this graph, the maximum infiltration rate is represented by this graph, right? So this point is known as all the points on this graph is known as the infiltration capacity. It is the maximum infiltration rate at that particular time. So this is the infiltration capacity, and final steady this value, and the initial value is f naught here, and the decay constant is represented by minus kh. And we are going to look into how to do these calculations when I switch over to the calculation sheet. So right now, just understand that we have to take the logarithm each side and then transform this equation in the form of y equal to mx plus c, where m is the slope, and that in fact is the decay constant, and c is the intercept, the y-intercept, or the infiltration rate intercept. So with this, let's see the question. Our question says, in a double ring infiltrometer test, a constant depth of 100 mm was restored at every time interval. The level dropped as given below. Okay, so time is given, water depth, so that much water has dropped, because once they have kept it 100, again it drops, again they are going to put it 100, and again the water is going to get infiltrated. So that is how the data is given here. It depends, okay, different people may take differently, so you need to read the question carefully. And first question says, establish the infiltration of the form developed by Horton. So what they're asking us is to find the parameter intercept. and the decay constant. If we have the decay constant and the intercept value, then we can simply plug in that value into Horton equation and we get that Horton equation. Okay, so that is what the question is asking. The next question is, so along with Horton's equations, we are also been asked to model the cumulative infiltration in the form of F, where the F is the cumulative infiltration is equal to A T raised to power N, whereas A and N are the some arbitrary constants. Okay, this A and N, the main objective is to find the value of A and N. And likewise there is another equation, F is equal to A T raised to power N plus an intercept C. So this is the question. So let's head over to a calculation sheet and then do the calculations. Okay, students, so let me quickly write down the question in a tabular form so that we can do the calculations. So here, start off with the time, because first thing that is given to us is time. So let me make a column with time and note the time here. So 0, 5, 10, 15, 25, 40, 60, 75, 90, 110 and 130 minutes. So this time is in minutes. We have to be very careful about the units here, because if we are not careful about the unit, then our calculations can go pretty wrong. So the next information given to us is the depth, the infiltration depth. Yes, so let me just write it as a D, or I can also could have represented it as I, whatever you like it. So first is at 0 time the depth was maintained at 100. So this is already given in question, so 83. So let me simply copy the question here. 83. Next is 87, 90, 85, 78, 85, 85, 85, and 80. One more, 80. So this is the depth. So actual now this is the depth that was maintained, right? So after there is an infiltration, that much depth was measured. So this is not in fact the infiltration. So infiltration would be the 100, because they are always maintaining the water level at 100. So the infiltration, now I'm representing infiltration in mm. So infiltration would be the depth 100 minus whatever the value is here. So first one is going to be 100 minus 100 is going to be 0. Second one is 100 minus 83 is going to be 17. Likewise 100 minus 87 is going to be 13. 100 minus 90 is going to be 10. 15 is going to be 22, right? 22 is going to be 15. 15, 15, 20, and again is going to be 20. Okay, one more important thing that we need to write here is the delta time. Not the delta time, but the delta t. See, the delta t for the first is 5 minutes. Likewise second is 5 minutes, right? 5 minus 0 is 5 minutes. So 10 minus 5 is 5 minutes. 15 minus 10 is 5 minutes again. But 25 minus 15 is 10. So delta t is not constant. So we need to, it would be wise to keep this delta t here, because else it's going to be tedious for us to do the calculation. So first I'm just keeping it blank. For next it is 5 minus 0, right? So this 5 minus 0 is going to be 5 minutes. So here it is in minutes. So 5 minutes is going to be again 5 minutes, is going to be 5. Yes, so 25 minus 15 is going to be 10, and again it's going to be sorry, this is not 40, it is 45, so I'm erasing this time. I made a mistake here. So this is after 25 minutes, then they are recording at 45, so which makes this time interval 20, then it is 15, right? 60 minus 45, again it's going to be 15, again it's going to be 15, then it's going to be 20. 110 minus 90 is 20. 130 minus 110 is going to be 20 minutes. Okay, so this is in minutes. Now let's calculate the infiltration rate. So infiltration rate, I'm writing this as F, capital F, and the unit is mm per hour. Okay, so unit is mm per hour. So how do we calculate this infiltration rate? Infiltration rate is where this is infiltration rate, right? Infiltration rate. So how to calculate? So infiltration rate is the amount of infiltration that is occurring in particular duration. So for the first case, it is 17 mm has infiltrated in 5 minutes. So this is going to be some values, right? Is going to be some values here. 17 divided by 5. But the problem here is our unit is, we have messed up the unit. If we take this unit, is going to be mm per minute. Is going to be mm per minute if we simply divide it by this 5. So if you have taken your first assignment or first tutorial seriously, I've given plenty of exercise whereby you are given the opportunity to do this kind of unit conversion. So here we need it in mm per hour. So how to convert this mm per minute to mm per hour? So what we do is we keep the infiltration, because it's in mm only, mm, fine, divided by how much is 5 minutes in hours. So 5 by 60, right? So ultimately we are going to get 17 over 5 into 60, so whatsoever the value is. Okay, so this is how do we do the conversion. So let me quickly erase this stuff now. Okay, so here it's going to be, for the first it's going to be, I'm putting a dash, for second it's going to be 17 over 5 into 60. For next is going to be 13 over 5 into 60. Okay, so the value is 204. The next is 156. Likewise, it's going to be 10 over 5 into 60, right? It's going to be 120. Yes, 5 12s are 60, so 10 12 is 120. Likewise, now let me only write the values from here on. So it's going to be 15 divided by it's going to be 15 divided by 10 into 60. Okay, let me write this for the last time. 15 divided by 10, because the delta t is 10, into 60. So 15 6 are 90. Okay, so here on I'm simply going to write the values now. So it's going to be 66 for this value. Now, okay, so did I messed up here? Okay, this is for this one, 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 and this is for this one. So for this one I'm going to write it here. So 66, 60, 60 again, and again 60, again 60, right? So again is going to be 60. So this is the infiltration rate. Now here, what we need to understand is, if you plot this graph, you're going to get this form of graph. Okay, if you put this infiltration versus time, so if you are going to plot this infiltration rate versus time, you're going to get something like this. Okay, so the initial value, the infiltration rate is f naught, and later is the fc, right? So from this table we can know that this value is our f naught and this value is our fc. So this much is already, now we have got the value for f naught and fc. Okay, so now let me also erase this. Okay, so here, to fit in Horton's curve, what we need is, let's write down the Horton's equation first. Okay, so let me write down this Horton's equation first. This is number 1, right? So Horton's equation is given by is f, this is the function of time, is equal to fc plus f naught minus fc exponent raised to minus kht, where t is the time. So f naught, fc, f naught we have already got from the table, right? So only unknown variable is now kh. To find the value of kh, what we are going to do is, let us first take this fc this side, left hand side. So it's going to be f, so I'm just removing this t. Okay, f of t, we need to understand that it's a function of time, minus fc is equal to f naught minus fc multiplied by e raised to minus kht. Okay, now taking the logarithm, taking log on both sides, we have, I'm taking natural log, so ln f minus fc is equal to, so it's going to be ln of f naught minus fc minus kht. Now if you closely look this equation, it is in the form of, this equation is in the form of y is equal to minus mx plus c, where m represents the k. This equation is the equation of a straight line. Okay, and how to get the value of k is, if you plot the y versus, right, this y versus this x you need to plot. Yes, so here x represents the time t, so you plot time in the x-axis, and in the y-axis you need to plot ln of f minus fc. So if you plot this two figure, we are going to get something like this. Okay, we are going to get this line. So slope of this line is in fact the value kh. Now how to find the slope? Now if you simply take these values, right, these values, ln of all these values, and plot it against time, then draw the best fit line and you should be able to get the values. You should be able to get the slope. But manually how you need to do is, you need the value of ln f minus fc. This value is required. this value is required. So we go back to the table and we make one more column. So let me draw a line here. So let me draw a line here. Okay, so here I'm going to write ln f minus fc. So fc is 60, f is this value. Okay, this column is the f, right? So for the first time is going to be ln of 204 minus 60. So this value. For the next column, next value is ln of 156 minus 60, the value. Okay, so let me write this value. So I have already calculated this value, and let me quickly write it down. It's going to be 4.970, and it's going to be 4.564. okay, so here I'm simply going to write the direct values. Okay, it's going to be ln 60, 120 minus 60 is going to be 60, so the value is 4.094. the next value is going to be next value is going to be ln of 90 minus 60 is going to be 30, so that is going to be 3.401. okay, likewise the last value is going to be ln 6, and is going to be 1.792. all this value is going to get us ln of 0. okay, so it's not defined, so we cannot calculate this value, so just leave it blank, not required. Okay, so we have these values. Now like I said, this kh is the slope of the line, right? This, if you plot this against time t, then the slope represents the kh value. So how to calculate the slope? The slope is change in y divided by change in x, which is, so let me take the change in y is, so I'm simply taking this value and this value, okay, last and the final value. So I'm going to take it as the last value is change in y, so it's going to be 1.792 minus 4.970 divided by the time is this time 1.72 value corresponding time corresponding 1.792 is 45. okay, so 45 minus the first, that is 5. this is in minutes, so you have to divide it by 60, so you're going to get, so what you're going to get is, let me see, calculator, so it is 1.792 minus 4.970 divided by 45 minus 5 and multiplied by 60. So it's going to be minus 4.767. so we got our value, that is slope is minus 4.767. So we have solved the problem now. So our Horton's equation is going to be, the main Horton's equation is going to be f of t is equal to fc is 60, right? 60 plus f naught minus fc. So f naught is 204 minus 60. 204 minus 60 e raised to power minus of 4.767 times t. So we have solved the problem. So this is how the problem is solved. Okay, and what we can do is we can also solve this problem with the help of a spreadsheet. So that's what I'm going to demonstrate next. Okay, so let's head over to a spreadsheet and do the same calculation with all the graphs, plotting, and so many other stuff to make it more intuitive. Okay, I hope it was clear, and let's head to the spreadsheet program. Okay, so we are here at the spreadsheet program, and I have already filled up the columns with the necessary information for our calculation. So first column is the time in minutes already given, infiltration depth that we have calculated previously, and delta t. As you know that the delta t is the duration or the time gap is different, so it would be wise to put it in a separate column because we need this value. And also delta t in hours, so I have converted that minutes in hours, and sorry, time in hours as well as the delta t in hours. So in my the hand calculation session that time I explained that for us to be able to model the to calculate the Horton's parameter, we need the value of ln of f minus fc. So this is required, right? And for that we also need, we need the value of the f, that is infiltration rate, per hour. Okay, this is it. So the infiltration rate is given by the infiltration depth, it's in divided by delta t. Okay, delta t in hours. So we have it here. So let me just drag this down. Okay, so we have the infiltration rate now. Now first value represents the initial infiltration, that is f naught. So let me mark this with a different color so that it becomes easy for us to identify. And fc, this is the value of fc. Okay, so likewise let's quickly do this calculation. Equal to ln of this minus 60, because fc is 60, right? That is what we have said here. This f naught, this fc. Okay, so let me drag this, and for after some values, when you minus 60 minus 60 is going to get ln of 0, which is undefined. So just delete this, get rid of this. Okay, first thing that we need to understand from here is, if I plot the time versus infiltration, we should be seeing a decay curve. So let's see that whether we are getting a decay curve or not. So I'm selecting time axis, time column, and the infiltration rate column, and let me insert this quickly. Insert chart, and I don't want column, I want x, y. So you see, this is the beautiful chart that you are going to get. So this is the infiltration rate curve. Okay, and by mathematical manipulation, we said that if you supply the logarithm on both sides of the Horton's equation, then you are going to get the equation transform in y equal to mx plus c form, where this y is equal to ln of f minus fc. So, and I also said that if you plot this value with respect to time, then you should be getting a straight line. So if we don't get a straight line, then we have made some mistakes. So let's check it out whether we are going to get a straight line or not. So I'm selecting only this values. Okay, now when I insert this, I should be getting a straight line. Let me see. Yes, I get a straight line. So also let me see the equation here. So insert the trend line, show the equation, and this equation is in the form of t. The variable is time t, and this is f of t. Okay, so fine. So here we have obtained the equation. See, this is the equation, and from this equation we know that the slope is minus, so the slope, let me write it here, SLOPE, slope is, or the decay coefficient minus kh is equal to, is minus 4.732 or 175. Okay, so let me keep it here. So this is the value of slope, or the Horton's parameter kh. Okay, so we have obtained the value of kh. Now the final thing that we must always do is check whether our answer is correct or not. So what we are saying is, let me put it here. So what we are saying is, this is the actual infiltration. So by modeling, what does the modeling means is we are trying to replicate this actual with the help of some equation, and that equation was provided to us by the Horton. So let's see whether the Horton is able to replicate the original or not. So for that, what I'm going to do is I'm going to bring this time, copy, and put it here, paste, oops, paste as value number. Yes, so this is, anyways, this is time, right? So I'm just putting this as a time, and this is the actual, ACTUAL, so actual. So I'm simply copying this actual value. Okay, so copy this and paste it. Oops, copy this and paste it, paste as number. Yes, so, and then Horton. So Horton's equation. So Horton equation, as we know, it is represented by f of t is equal to f of c plus f naught minus fc times exponent raised to kh times t. So let's try to do that. Is equal to 60, because 60 is the fc, okay, plus bracket open, then this f naught, right? F naught is always going to be 204 minus 60, right, times exponent of minus 4.73175 times t. So t is in hours, so let me put it here. So this is what Horton has given us. So basically this value, whatever the value we get, and this value, there should not be much deviation. Okay, so there should not be much deviation. A little bit of deviation is accepted, but it should not be a huge deviation. Let me keep it to this point. So there is some deviation, but the deviation is not much. So it would be interesting for us to plot this and see how it actually looks with in a graph. So let me plot this graph, and I want it in this form. So you can see here, let me minimize this a little bit. so that you can see this clearly. So you can see that the actual infiltration that we have got from the field experiment, and with the help of some parameters that we have derived from the field calculation, and we fitted the Horton's model, and Horton is also able to replicate what is there in reality. Yes, so there is not much of difference, but we see that it is underestimating for the initial phase, and later on it is coinciding with whatever actual value is there. So this is the main, that is the concept of modeling. Modeling means uh, representing, replicating the actual work with the help of some equations. So that's what a modeling means. So yes, we have derived the Horton's equation then. So thank you, this is it.